Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level to upper high school level physics questions. So here's our first one. A sports car is moving at a constant speed, travels 110 meters in 5 seconds. It then brakes and comes to a stop in 4 seconds. So we have two parts to this. The person who left the question also asked, what is the total time? In the solutions, the total time is 4 seconds, but as it is supposed to be 9. So don't get confused by the way they phrase the questions here. So there's really two parts here. So first, we travel a delta x of 110 meters in a time of 5 seconds, or a delta t, and so our velocity is delta x over delta t, which is equal to 110 meters over 5 seconds, which is 22 meters per second. And then we use this velocity in our second part, for which we are looking for the acceleration. We have an initial velocity of 22 meters per second, and we're stopping in a time of 4.0 seconds. And so now we can use our other kinematic equations, which are Vf is equal to Vi plus a delta t, where we want to use that Vf is 0. And so we can rearrange this equation to a is equal to Vf minus Vi over delta t, which is 0 minus 22 meters per second over the 4 seconds, which comes out to minus 5.5 meters per second squared. And it's looking for the magnitude of the acceleration, so we might as well finish out the question. And so the magnitude is the unsigned quantity, so just 5.5. Okay, so we'll check to the solution here. And they divided by g. I don't know why that would be, but okay. But everything else looks okay. Alright, so here we have a train moving at constant speed of 70 kilometers per hour. We might as well move this into meters per second, just because that's just always what we tend to work with here. So 1 times 10 to the 3 meters per kilometer times 1 hour per 3,600 seconds, which comes to 19.44 meters per second. So we have 3 directions that we're given here. So for our first one, it says that we move east for 46 minutes. So I'm going to go ahead and set up an axis system and say that and use XY, or I guess I might as well in this case use IJ. I'll just have to be consistent. So I hat, J hat for east, north, and then west will be negative I hat, and south will be negative j hat. So for the first leg, I'm moving due east, so my velocity is 19.44 meters per second I hat. My time is 46.0 minutes times 60 seconds per minute, which comes to 2760 seconds. And so the distance, or the distance vector that I've traveled, is VT, which is the 19.44 times the 2760 seconds, which comes out to be 53,654.4 meters in the I hat direction. Now for my second part, I'm traveling at an angle of 46 degrees east of due north. So that's my angle, 46 degrees. There's my velocity vector. And I can decompose this into V cos 46 and V sine 46. So my velocity is my magnitude, V times cos 46. No, I'll do sine first, sorry. Sine 46 in my I hat plus V cos 46 in my j hat, which is, so my velocity in this case is the same one, so 19.44. So I can put this in my calculator and get 13.984 and 13.504. And these are meters per second. Now the time I'm given for the second section is 21 minutes. Converting it to seconds is 1260. And so then my displacement is my velocity times my time. Which comes out to be of course the seconds will cancel here in the I hat direction, and this distance in the j hat direction. Okay. So then I'm just going to start circling these a bit just so I can find them later. And so then my third leg of the journey here is due west for 78 minutes. So my velocity is now my magnitude in the minus my magnitude in the I hat direction. So that's just what was my velocity here? Minus 19.44 meters per second I hat. My time is 78 minutes times 60 seconds per minute, which comes out to be 4680 seconds. So then my displacement is my velocity times my time. 4680 seconds, which comes out to be, where am I here? Minus 90,972. Oh, 979, sorry. 0.2 meters in the I-hat direction. And so now we get to the actual questions. So what is the average velocity and direction counterclockwise from east? So I guess it's looking for an angle. So our total displacement is each of our individual displacements summed. So that's our first one was 53,654.4 meters in the I-hat. Our second one was this guy. And our third one that we just calculated was this guy. So we just sum these all up, remembering that I-hats go with I-hats and J-hats go with J-hats. In this case, we only have one. So it comes to negative 19,704. Excuse me. All right. Okay, so that's my total displacement. And so my velocity, is going to be my displacement over my total time. My total time is just the sum of all my times. So we had 2760 seconds plus 1260 seconds plus 4680 seconds. And so this, when you sum them all up, comes to 8700 seconds. So my total velocity is my total displacement over my total time. So it's this guy. Over my total time, so 8700 seconds. And so then my total velocity vector comes to minus 2.265 meters per second I-hat plus 1.956 meters per second J-hat. And so the angle, just to sketch this out here, so we've got 2.265 in here, 1.956 in here. So then this angle is, so tan theta is equal to opposite over adjacent, so 1.956 over 2.265, which leads to theta equals 40.81. If we're looking for the angle that's counterclockwise from east, though, then we're looking for this angle, which I'm going to call phi. And so then phi plus theta is 180, which means that phi is 180 minus 40.81, which means that our phi is 139.19 degrees. And so then there's our average velocity and our angle counterclockwise from east. So if we check the solution, we get our total displacement, our average velocity, I guess I could have done the magnitude. I would say that's average speed, but if I'm going to do the magnitude, I can do that as well. So my magnitude of my velocity would be the square root of 2.265 meters per second squared plus 1.956 meters per second squared. So just square the individual distances or the individual components. And for this, I'm just going to have to open up a calculator and say 2.265 squared plus 1.956 squared equals, and then root. So then our velocity, our speed, our average speed is 2.99 meters per second. Which, if we compare to what they found here, about 3, that must just be rounding differences. And the theta, in their anti-clockwise theta from east, they got was 140 degrees. We got 139. So again, I assume that's just rounding differences. So that looks good. Okay. All right, so we've got 3 forces. And a free body diagram. So we've got X. I'm just going to re-sketch this, just I have something to work with. So here's our y direction, which also has a force F2, which is equal to 200 newtons. We've got our F total, which is at a theta prime equals 60. We've got an F1, which acts at some angle from our F total. I believe our F total is given as 800 newtons. And we've got an F3. Drawing straight lines is not my forte this morning. F3, which is 180 newtons. And it's given, we're shown a similar triangle on the vector, which is a 12, 5, 13 triangle. Okay, so first of all, I'm going to drop that there and say that's phi. And so let's figure out all our vectors here and then figure out what our total would be. So our F1 is, our F1 vector is going to be our F1 magnitude times our cosine of phi I hat. So that's going to be my my x unit vector plus F2 sine phi j hat. My F2 force is straight up, so it's just my F2 j hat. So that comes to 200 newtons times j hat. And then my F3 is, again, I'm going to just call that angle gamma. And so we can see that it's minus 180 newtons times cosine of gamma in the I hat direction plus 180 newtons sine gamma in the j hat direction. So we can solve for our angle here, or we can solve for the values directly. So we're shown for F3 a 12, 13, 5 triangle. So that means that cos gamma, and this is gamma in here, cos gamma is the adjacent over the hypotenuse, so 12 over 13. And sine gamma is 5 over 13. So again, we could solve for gamma, but we actually already have our values. So F3 is minus 180 times 12 over 13. I hat plus 180 times 5 over 13. So we don't need to bother actually solving for the angle there. Now we can get our total vector by looking at the triangle we're given there. So we're given this one, where that's 60 degrees. There's our F total, which is 800 newtons. And so we can see that this side is F total cosine of 60, and this is F total sine of 60. So our F total vector is Ft sine 60 in the I hat plus F total cos 60 in the j hat, which is 800 newtons. Times the sine of 60 is root 3 over 2. And the cosine of 60 is a half. Okay, so now we have each of our vector quantities. I didn't do F1. We'll just have to solve for its components. And the best way here is to look at the directions separately. So in our x hat, well, first, I guess I should just start by saying that remember our F total is just the sum of our forces. So if we look in just the x hat in the x direction or the I hat direction, so just take the I hat components. We have 800 newtons times root 3 over 2 is equal to our F1, which is just F1 cos phi, plus our F2, which is 0 in the x direction, plus our F3, which is minus 180 times 12 over 13. And so we can rearrange this and say that F1 cos phi is equal to 800 times root 3 over 2 plus 180 times 12 over 13. I could work this out, but rather than working completely in decimals, I figured I would just leave it. Now in the y hat direction, or in the y direction or the j hat direction, we have 800 newtons times 5 over 13, times a half is equal to F1 sine phi plus 200 newtons. And so that's the F2 component, and then the F3 component is 180 times 5 over 13. So then we can rearrange this for our F1. Say that F1 sine phi is 200 there we go. Is 800 newtons divided by 2, which is just 400 newtons. So I'm working that one out because then I don't have to worry about the decimals. Minus 200 newtons minus 180 newtons, 5 over 13, which is, and I can do that subtraction pretty readily. And there we go. Okay. So now I have two equations here and two unknowns. So there's my first equation. And here's my second equation. And I'm just going to divide the second equation by the first equation, which will give me F1 sine phi over F1 cos phi equals 200 newtons minus 180 newtons times 5 over 13 over 800 newtons root 3 over 2. Okay. And now, now I actually need to do some of this, but first let's cancel out these F1s. Sine phi over cos phi is tan phi. And now if I work this out on my calculator, the numerator here gives me 130.769 newtons, and the denominator becomes 858.974, which gives me a phi of 8.656 degrees. And then my force, I can use either of the equations. So I can say that F1 times the cosine of 8.656, which would be the first equation there, is equal to 400 newtons. It's equal to, I'll just again keep it all worked out here. So it would be this 858.974 newtons. So then my F1 comes out to be 868.871. Okay. And then, so I've got my force, I've got my phi. So there's my my value for F1. If we look at the figure though, it wanted, so there's my 60 degree. It wanted this theta, F total, F3. And so we just calculated this angle. And so then recognizing that that's a 90-degree angle, so 60 degrees plus theta plus phi is equal to 90. So then theta is 90 minus 60 minus phi, which is 30 minus this 8.656, which comes out to be 21.344 degrees. And so there's the F1 and the angle they were looking for. So about 869. And the angle is about 21.3. So that looks good. Okay. So here we have a box of money on a frictionless inclined plane at 37 degrees. So just drawing out this diagram, mostly based on what's given in the solution here. So we've got an M1 of 3.4 kilograms, an M2 of 1.4 kilograms, connected by a frictionless pulley. So this angle in here is 37 degrees, and this angle in here is 59 degrees. And it wants to know what the tension is in the string. So to start off, I'm going to draw a free body diagram for our M1. And so we've got our mg and our tension, and then a normal force to the surface. And I'm going to go ahead and define my axis system as running along the surface. So there's my x and my y. And so the tension is going to be completely in the x direction here, but we just need to decompose our mg force. So just drawing this out again, this triangle here. So we've got a 37-degree triangle, and our mg is going to act straight down. And the similar triangle there, it leads to that being 37 degrees. And so then, if that's 37 degrees, then our mg force is equal to mg cosine of 37. Nope, sorry. I'm just going to do this properly, or the way I would normally do it. So minus mg, so the x direction is going to be acting downwards, so minus mg sine of 37 degrees I hat, and then the y direction will also be acting downwards, so minus mg cosine of 37 j hat. Okay, so then looking at my x and y components, so in the x direction we have f net x is equal to my tension is in my positive x direction minus mg sine 37, and that's going to equal m1, I should say, times my acceleration in my x direction. So we haven't been told whether there is an acceleration, but we should probably assume one. If I look in the y direction, then I would find that our f net y is just the normal minus the mg cosine of 37. And since it's not moving, that's going to equal 0. Not moving in the y direction, I should say. So our normal, we could solve for our surface normal this way, but we don't need it because it's frictionless. Okay, but we will need this equation, and we can see that we have one equation here, but two unknowns. So now if we look at the other mass, our M2 mass, and we draw our free body diagram. So we have our tension and our mg force and our surface normal. I'm going to go ahead and define my axis system, and just so that it's moving in the same direction, I'm going to have x going down the slope and y going up the slope, or y going away from the slope. Going in the same direction as far as the positive direction of acceleration will be in the same direction here, so we don't have to worry about weird sign stuff. So again, sketching out our triangle here. This is a 59-degree angle. Our mass, our mg force is straight down, which if we draw our similar triangle, that's our 59-degree angle. And so then now we can see that with our axis system drawn up top, our mg sine of 59 is going to be in the positive direction, and our mg cosine of 59 is going to be still in the negative direction. So if we look at our x force, our F net x is mg sine 59, m2g sine 59 I should say, minus our tension, so our tension goes in the opposite direction, is equal to m2 times our acceleration. And again, just for completeness, our F net y will just relate our surface normal to our mg force. Okay. All right, so now we have two equations and two unknowns. I'm just going to restate them just so that we have them. So we've got we've got t minus m1g sine 37 is equal to m1ax, and we've got t I can't do this here, m2g sine 59 minus t is equal to m2ax. So let's go ahead and divide out the masses in the two equations here. So our first equation becomes t over m1 minus g sine 37 degrees is equal to our acceleration x. And our second equation becomes g sine 59 degrees minus t over m2 equals our acceleration x. So now we can subtract these two equations to get that t So if we subtract, we're going to have m1 over m1 plus 1 over m2 and minus g onto sine 37 degrees plus sine of 59 degrees. And that will equal 0 because ax minus ax will give us 0. So then we can solve for a tension as by rearranging this. And now we can place in values. So then our tension is 9.8 meters per second squared. If we sum that up, that's 1.45898. Our mass 1 was 3.4 kilograms. And our mass 2 was 1.4 kilograms. So this comes out to be 14.179 newtons. So then there's our tension in the cable. And then if we check the solution here, it comes out to 14.17, so that looks good. The only difference would be in some rounding stuff, but that's okay. So there's our solution. All right. So in the figure here, we're given a plot of electrostatic potential along the z-axis, and we want to plot or sketch out the E field. So I'm not going to be able to do this perfectly without some kind of graphing software, but I'll do my best. And really, we just want to sketch out the relationship between the potential and the E field anyway. So this is probably not varying in a continuous way, but that's okay. And it might be at a bit of an angle. All right. I feel like I can't help but draw things at a bit of an angle here. All right, so there's my V equals 0. Okay. Yeah, so I'm definitely at an angle, but all right, maybe I'll resketch it just to see if I can make it a little straighter here. All right, I think that works. Okay, and this should go down to 0. All right, so then the real point here is if this is my potential, and if I recall, I like to use this little box here, so I can get from my potential energy to my force by multiplication by minus the del, or the derivative vector. I can get from potential to potential energy by multiplication by Q, the charge, and I can get from potential to E field by multiplication by my derivative vector. Now here I'm just talking about the Z direction, so my E field is just the minus derivative of my potential with Z. And so I can identify and to sketch out my E field, I can identify a few key points. Also, to get some values here, so this is given as 1, that's given as 0.8. So to get some values, I can use kind of rough estimations. So I believe the time or the distance, sorry, in here is about 2 meters. So it looks like my delta V over delta Z in that region is, say, about 1. So I would presume that I'm going to peak out at about 1 in here, and go down to, now I haven't drawn it to the same kind of scale here, but it does look like over here, my delta V over delta X is about 0.8 to negative 0.6, so about 1.4 over about 2, so about 0.7. So I would assume my E field is definitely going to decline the same way as my potential is declining, but we just need to identify some pieces here so we can sketch it out. So first of all, at each of the turning points, my dV by dz is 0, right? So these are the points where my derivative is 0. And so my E field will be 0 at these points. And I'm going to do my best to try to drop these down to this lower plot, because these should be my 0 crossings, and it's going to guide my sketch. Okay, so these points will be my 0 crossings, and then I really need to just join them up in between. My maxima are actually going to occur where the 0 crossings are, but remember my E field is minus dV by dz, meaning this point here, so the derivative here will be negative, so this will actually be my positive. My derivative here is positive, so this will actually be negative. So my E field will be maximally negative here, fairly maximally negative, positive there, negative here, a little bit reduced, positive here, a little bit reduced, negative here, a bit reduced, and here will be a bit positive and negative. So here's my kind of my points. They've compressed a bit. I don't think it's supposed to be this there's supposed to be a time variance here, but there. So that's my rough sketch here. The real things that we should notice, or if you use the graphing software you definitely would notice, is just well, the E field's the negative derivative of the Z, and so it's a bit shifted from the potential field, or from the potential. It crosses 0 wherever the derivative is 0, so at each of the turnarounds. And then where the potential crosses 0 is where our maxima are. And then the specific values would just be, well, this would be something like 1, and over here it would be something like 0.7 probably. But that's just a rough estimate. If you wanted to do it fully, you would want to use some kind of graphing software. And here there's no solution, so this is just incomplete. Okay. So here we have a rock is thrown vertically upward. from ground level at t equals 0 seconds. So I'm going to assume that my rock is being thrown from y equals 0, t equals 0, and so it's thrown with some velocity. At t equals 1.5 seconds, it passes the top of a tall tower, and then 1 second later, so t equals 2.5 seconds, it reaches its maximum height. So what that means is that my velocity is 0 at that point. Okay, so then we're not given the velocity with which it's thrown. We're just told that in 2.5 seconds it comes to a stop. So we can look at some of our kinematic equations here. So our YF is our YI plus a half VIT, no equals there, plus AT. So our acceleration is always going to be gravity, so minus g. So we have that. And I've gotten myself a little confounded here. So that's not a half, that's a half. And that should be squared. Okay. So we don't have our velocity. But if I look at my velocity equation, so VF is VI plus AT. This one we do have. So we don't have our VI, but we know our VF at the 2.5 second range. So we could say that our VI is minus AT. So our VI is minus G times our 2.5 seconds, which is 9.8 meter per second squared, times 2.5 seconds. So our initial velocity is 24.5 meters per second. And so then now we're in a place to calculate the height of our tower using our 1.5 second time. So now our YF is equal to our YI plus our VIT plus our 1/2 AT squared. Our YI is 0. So we're going to use our 24.5 meters per second speed times our 1.5 second time. And we just need to subtract. So our acceleration is minus 9.8 meters per second squared times our 1.5 second time squared, which comes out to be 25.725 meters. Okay, so if we check the solution, we first need to get our velocity, which is 24.5, and then we can use that velocity in this equation to get 25.7 meters. So that looks good. Okay, so we have a vertical container with a base area, so it's a cube. And our base area is 15 centimeters by 18 centimeters. So our area here is 15 centimeters by 18 centimeters. And we're filling it with identical pieces of candy. So each candy has a volume of 50 millimeters cubed and a mass of 0.02. And now we're going to assume that the volume of the empty space between the candies is negligible. And if the height of candies in the container increases at a rate of 0.28 centimeters per second, at what rate, kilograms per minute, does the mass increase? Okay, so our I'm going to call the M for the individual candy is our 0.02 grams. And our volume for our individual candy is 50.0 millimeters cubed. So our total volume for our candy, in terms of the question here, is going to be our base area multiplied by our candy height. Which and our total mass of our candies we can write as our individual candy mass over our individual candy volume times our total volume of our candy. And just writing it in terms of these quantities that I've written out. So now what I want is my rate of change of my candy mass with time. And so the only thing that's changing with time here is the height. So these are all going to be just constants. And we're given the height change with time and actually pretty much everything that's in this equation here. So this is just going to be my individual candy mass over my individual candy volume times my area times my change with height in time okay. And now we either need to convert centimeters to millimeters or millimeters to centimeters. So I'm going to go ahead and multiply this whole thing by 1 times 10 to the 3 millimeters cubed per centimeter cubed. So that'll convert my centimeters to millimeters, canceling those out and leaving us with grams. So then this is 330.24 grams per second, so grams per second, which we can multiply by 1 times 10 to the minus 3 kilograms per gram to put us into 3.024 times 10 to the minus 2 kilograms per second. And actually they want it in minutes, so let's go ahead and multiply by 60 seconds per minute, which is 1.8144 kilograms per minute. All right, so looking at the solution here, so we can define a density, and then we get our mass, change of mass with time, putting in the values. Wait, what? Oh, 0.3024 kilograms per second. So it does ask for kilograms per minute, but I would say that conversion is not super necessary. Question asks for kilograms per minute, which is 1.8144. I'm just going to say this one's correct because a small unit conversion at the end isn't that important. Okay, so here we've got a particle of charge Q. Q equals minus 8.7 microcoulombs, sorry. Has a velocity of 625 meters per second, and it lies in the XY plane. And makes an angle of 65 degrees. So there's my V vector. And so there's V cosine of 65 and V sine of 65. So my velocity vector can be written as 625 meters per second cosine of 65. That's going to be xy. I hat plus 625 sine of 65 j hat, which comes out to be 264.136 meters per second I hat plus 566.442 meters per second j hat. Okay, so there's my velocity vector. I haven't finished reading the question here, but I figure we're going to need its components. So it makes an angle of 65 degrees with respect to the x-axis. So there's our velocity vector. We've got a constant magnetic field in the y direction. So there's our B, and it equals 1.6 Tesla. What are the magnitude of the magnetic force on the particle? So it's looking for magnitude, but we can get direction as well. So F is QV cross B. So the way that I usually remember to do this here is with determinants. So this is minus 8.7 times 10 to the minus 6 coulomb. And the way you do this with determinants is by having our x, y, z, and then you place the velocity in here. So 264.136 meters per second, 566.442, and 0. Our B field is 1.6 Tesla. And so we take the determinant of this matrix, and so the determinant comes out to be, well, I'll use I hat, J hat, K hat in retrospect, just to be consistent. All right, so in the I hat direction, we have 566.442 times 0. So it's this, minus 0 times 1.6. So that's just going to equal 0, obviously. Minus j hat times this. So that, again, is just going to be 0. I'm not going to bother writing these all out, in fact. So this is just going to be times 0. That's times 0. And then plus k hat times, so in the k hat direction, we've got this minus this. So we can see that the minus is going to be 0, but we've got 264.136 times 1.6 Tesla. And so then that equals, so then the I hat goes to 0, the J hat goes to 0, and all that's left is the K hat. And then we just multiply these things up. and we get minus 3.6768 times 10 to the minus 3 newtons in our k hat direction. If we're just looking for magnitude, so the magnitude of our force is just 3.6768 times 10 to the minus 3 newtons. So obviously we could have, right from the get-go, said that our force is just going to be, because the B field was in the J hat direction or in the Y direction, we could have just multiplied our X velocity by our B field in the J to get our force in the K. So there's or alternatively, as they've done, we could have expanded the cross product as a sine theta and determined the angle between the two. And so that could have been done as well, which is what this person did. And so this is still correct. Okay, so we've got a tennis ball initially moving with a velocity of 28 meters per second to the right, and a tennis racket strikes the ball. So a tennis racket, we've got some velocity VR, and then we're going to strike the ball. I'm actually just going to draw it like this. And the ball is going to leave at 28 meters per second. And then presumably our racket will be forced backwards. And so if we treat the collision as perfectly elastic, and we treat the ball as a particle of mass 0.0580 kilograms, and the racket as one of 0.261 kilograms. So the first question is, does the speed of the racket change as a result of the collision? So first of all, so if it's an elastic collision, then our delta KE is 0. So our initial kinetic energy is 1/2 the mass of the ball times the velocity of the ball squared, plus 1/2 the mass of the racket, the velocity of the racket squared, or the speed of the racket squared, I should say. So, and then our KE final. I'm going to put little I's on this to say that these are the initials. The speed of the ball final squared plus 1/2 mass of the racket, velocity of the racket final squared. Okay, so if our delta KE is 0, that means that our KEI equals our KEF. So 1/2 mass of the ball, velocity of the ball initially squared, plus 1/2 the mass of the racket, velocity of the racket initially squared, Now, we're given that the speed of the ball, it's changed directions, but it's 28 meters per second in both cases. And we don't need to worry about the mass because we can see here that as the mass isn't changing, that these guys are actually going to cancel, leaving us with 1/2 mr VR initially squared is equal to 1/2 mr VR finally squared. And obviously these 2's will cancel and these masses will cancel, and we can take the square root and find that our velocity of our racket initially is equal to the speed, I shouldn't say velocity, the speed of our racket finally. So our speeds are constant. So for A, the speed does not change. All right. So for B, it asks what the total momentum of the system is. So P total, we can either do it initially or finally. So we could use mass of our ball, velocity of our ball initially, plus mass of our racket, velocity of our racket initially. And this is actually a vector quantity, so let's throw those in there. And so I'm not sure how to do this without actually knowing our racket's velocity. So use our final momentum, which is mass of a ball, velocity of the ball finally, plus mass of our racket, velocity of our racket finally. And so we know that PI equals PF. I'm just gonna change that from total to I. Or mass of our ball, velocity of our ball initially, plus the mass of our racket, velocity of our racket initially, is equal to mass ball, V ball finally, plus mass of our racket, velocity of our racket finally. So we can rearrange this equation to just bring each of our components on either side. So VBI minus VBF, mass of racket, VRI minus, or VRF minus VRI. And we can see here, and we know that our VRF is equal to our VRI, so our magnitudes are equal. But on the left here, we can see that we have mass of ball times minus or plus 20 meters per second. Oh, sorry, 22 meters or 28 meters per second. And then the final speed is a minus 28 meters per second. So then on the left, it's non-zero. So then I'll just leave this in like this. So on the left, it's going to be non-zero. In fact, it's going to be MB times 56. And so our velocity finally for our racket must be the negative of our initial. And so then this would be minus VR initial minus v our initial, or our racket's initial velocity must be minus mb over mr times 56.0 meters per second divided by 2 as well, because there's going to be 2 of them. Okay, and so then our racket's initial velocity is minus the mass of the ball, 0.0580 kilograms over 2 times the mass of the racket, 0.261 kilograms, times our 56.0 meters per second, which comes out to be 6.22 meters per second. So our initial velocity of our racket is minus 6.22 meters per second. And so then the total momentum is just one of the two, either initial or final. So we can use the initial. So it'll be mass of ball, v ball initial, plus mass of racket, v racket initial. I'll put these where I had them before. And so that's 0.0580 kilograms times our velocity initial for a ball, 28.0 meters per second, minus 0.261 kilograms times our 6.22 meters per second. So I guess plus, and I'll put the minus in here where it belongs. If we work this out on our calculator, it comes to 5.8 times 10 to the minus 4 kilograms meters per second. So that's the total momentum for our system. Again, I don't know how I would solve for the total momentum without knowing that velocity. Except in a roundabout way, but it's easier to solve for the velocity before the momentum, I would think. But oh well. So here we go. So if we check through the solution here, the speed of the racket doesn't change as a result of the collision, so that's good. Determining the total momentum. So we can either use, so here they've used the finals, and the final speed of the tennis ball is 28. They've set it to 0, but that doesn't make any sense, because if the speed isn't changing, then why would it be 0? That sounds like the speed is changing. And so the total momentum is 1.6, so that's a little high, since I've got 5.8. And then using their total momentum, so they're saying, so right here it's saying that the initial velocity of both is just the final velocity of the ball, but if the speed of the racket isn't changing through the collision, then they're representing the speed is changing. So yeah, so part B and C are done incorrectly. Speed of racket doesn't change through collision. So if the racket speed doesn't change through the collision, then it can't go to 0. That doesn't make sense. Okay, so here we have an air bubble at the bottom of a lake. I probably didn't need to do it there, but whatever. and it's 40 meters deep. So then the pressure on the air bubble, or at the air bubble, is rho, so the density of water. Sorry, let's start over a little bit here. So the pressure is going to be 1 atmosphere plus the force over the area. So the area here is, and so we've got the force due to all this water is going to be mg, where m is our volume of water times our rho, so our density of water. So this is V times rho times G over our area. But of course, volume is area times height. So our pressure is 1 atmosphere plus rho G H. So for rho, I'm going to use just 1, and so the pressure for the bubble 40 meters below the surface is 1 atmosphere plus 1 times 9.8 meters per second squared times our height, which is 40 meters. And that's 1 kilogram gram, 1 gram per liter, or 1 gram per decimeter. Oh, sorry. I'm not going to use 1. Now I see what I wrote there. 997 kilograms per meter cubed is what I'm going to use. There we go. Okay, so now my units are a little bit funny here. So this is going to give me 1 atmosphere plus 390,824 pascals. An atmosphere is 101.325 kilopascals. So my pressure is 101.325 kilopascals plus 390.824 kilopascals, which is 492.149 kilopascals. There we go. Okay, so we've got a bubble at the bottom of a 40-meter lake. The temperature is 4 degrees. Celsius. And now for the second part, the bubble rises to the surface, and where the pressure is this 101.325 kilopascals. Our temperature is now 22 degrees Celsius. And so it asks what is our volume in this case. We are given in the question that our volume initially is 19 centimeters cubed. Okay. So using, we can use ideal gas law here. So for our initial case, we've got PV equals nRT. We've got pressure, volume, and temperature. So we can solve for nR. We know what R is, it's a constant, but we might as well just leave it in there because it's not going to change. So our pressure is 492.149 kilopascals times 19 centimeters cubed times 1 times 10 to the minus 2 meters per centimeter cubed over our temperature, which is 277.15 Kelvin. So our temperature is 4 degrees, which is 277.15 Kelvin, and our temperature here is going to be 290. So plus 273, so 295.15 Kelvin. So our nR in this case comes out to be 0.0337392, and this is actually in pascals meters cubed per Kelvin. So I did also multiply by 10 to the minus 3, or 10 to the plus 3 here. Okay, so then at the surface, we have PV equals nRT. Again, we want to know the volume, so our volume is nRT over our pressure. We can use our nR that we just solved for, so 0.0337392 pascals meters cubed per Kelvin. Our temperature is 295.15 Kelvin, and our pressure is 101.325 times 10 to the 3 pascals. So we can see that our pascals cancel, our kelvins cancel, and we're left with a meters cubed answer. So 9.828 times 10 to the minus 5 meters cubed, which we can put into centimeters cubed by multiplying by the relevant factor. So our meters cubed will cancel, and this will be 98.28 centimeters cubed. So the volume they solved was 101. I presume that's just differences in, so their temperature was they added 273, not 273.15, so that's going to change some things. They also use 10 to the 5 pascals equals an atmosphere, which is not quite right. They just use 5 atmospheres, so a lot of rounding differences there, but I think for the most part it's correct. All right, and I'm actually going to sign off there and say thank you all for watching. I hope you enjoyed this. If you do, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.